you ever thought of exploring other dimensions, or wonder what makes up the universe? Well, string theory can help you with that. But to understand string theory, or the theory of everything, we must first understand the atom. The atom is one of the most basic units of matter known to man. We know that the atom is made up of protons, neutrons, and electrons. These are all very important, but what makes them up? If we dive deeper into one of them, we will find that they are made up of quarks. These quarks come in 6 different flavors, and no, not like ice cream flavors, but types of quarks, which are up, down, top, bottom, charm, and strange. Up, top, and charm quarks are all positively charged, while down, bottom, and strange quarks are all negatively charged. And the pairs of quarks will cancel each other out, as seen here. String theory helps us explain what makes up quarks. According to string theory, these quarks are made up of tiny strings that vibrate at many different frequencies to create all of the quarks and give the different atoms their unique features. But even if we had the equipment to see things at that size, which is predicted to be less than a billionth of a billionth the size of an atom, we still wouldn't be able to see them. According to string theory, there are also 6 other spatial dimensions and 1 time dimension that we cannot comprehend to go along with the 3 dimensions that we already know. The dimensions of up, down, left, right, forwards, and backwards. There are theories about what these dimensions look like, and here it is. These are Calabi-Yau shapes. These shapes are predicted to be as small as 10 to the negative 35 meters, and as large as 1/10 of a millimeter. These shapes move in different ways, and their movements determine how strings act and look like. String theory also proposes that there is an opposite, or superpartner, to small subatomic particles. The superpartner of a fermion particle is a new particle that has the same name but begins with the letter S, such as the superpartner of an electron is a selectron, or the superpartner of a quark is a squark. The superpartner of a boson particle changes so it ends in INO. So the superpartner of a photon is a photino. Here's a list of other common superpartners and their names. So, in review, string theory is useful because it tells us what the universe is made up of in its smallest form. This is done through strings. The shape and movement of these strings is determined by the Calabi-Yau shape that they exist in. Subatomic particles also have a superpartner to counter them out. Overall, string theory helps us to unite the forces of gravity, electromagnetism, and both strong and weak nuclear forces into one unified explanation.